Hi, my name is Robert Feranek, I'm from Fedevel Academy, and in this video we are going to learn about via in pad. After you finish watching this video, you should have all the most important information about using via in pad in your own project. So after you finish watching this video, you should know, for example, what size of via in pad you need to use in your own board, what kind of or what size of drilling you need to use in your own board. You will know exactly how to use via in pad in your own project. And that's the goal of this video. Basically, what happened, I'm going to use via in pad technology in my own project. So I had to do all this research to learn more about the via in pad technology. I also talked to a PCB manufacturer, ask some questions, and all this information, my research and these questions about via in pad, all this I included in this video. So after you watch this video, you will know all the things what I learned, and after you finish watching this video, you will know how to use via in pad in your own boards. To give you accurate information about via in pad technology, I talked to Mike from Exception PCB. Exception PCB is a PCB manufacturer what I have been using for, I think, like more than 10 years. And I was very happy when Mike agreed to make a call which I could record and which I could use for this video. So in this video you will see some clips from our call with Mike where we are speaking about via in pad technology. Now, how all this started? How did I decide on using via in pad in my project? How you are going to decide if you should use via in pad or not on your own board. What basically happened in my case is I'm using this processor, and what we can see here, this is the reference design from the processor. And when I checked how they implemented this fan out, how they take out the signals from the processor, they use these vias here. The thing is, the pitch of this processor is quite small. If I measure it, you see it is 0.65 millimeter. And these vias, what they used to fan out these signals, they are only 0.35 millimeter. And these are quite small vias. So first thing what I wanted to know is if we can use this kind of via in our board, or if they are too small, or what should we do if in the reference design they use this kind of small vias. Can we manufacture, or can these small vias be manufactured? Can we use them safely in our board? And here is the answer from Mike.
We run with 3 mil. Obviously, yeah, 4 mil is would be better. Gives you a little bit more annular ring, so that would take up any slight deflection of the through via. But we certainly manufacture here to using a 3 mil ring, and it's quite common, to be honest.
Just a very quick interruption. When we will be speaking in the video in millimeters, I will put somewhere on the screen also the same dimension or same size in mils. Okay, so the numbers what you will see on the, or what you can see now on the screen, it is exactly same size or same dimension as we are talking about, but in the other units. So when we are speaking about mils, it will be in millimeters. If we are speaking in millimeters, then the dimensions on the screen will be in mils. Okay, let's continue.
Qualify that, Robert. Yeah, on the external layers, a 75 micron annular ring is good. Internal layers, yes, we would like to have 100 micron.
And now you may be thinking like, but I'm watching this video to learn about via in pad. I don't want to learn about vias. The thing is, via and via in pad, they are almost the same, okay? So the parameters or the limitations or the minimum size is what applies on via. You can apply them also on via in pad, or all this is very similar or almost the same. And that's why we are speaking about vias, how small vias we can make, because we would like to know how small via in pad we can make. Before we continue, I would like to be sure everyone understand what we were talking about in the previous two clips. I know sometimes even people what are just starting with hardware design are watching these videos, so I'm going to explain what we were talking about in the two previous clips. Basically, we were speaking about the ring, and ring in via is the part of the via, or is the size of the ring is basically the distance between the edge of the hole in via and the end of the via. Okay, so this is the hole in the via, this is the ring. And as Mike explained, the standard kind of smallest width of the ring, what they would like to have is, do you remember? 100 micrometers. Okay, so what is the kind of standard minimum size of the via? Do you know? Usually the smallest standard hole size what you can use in 1.6 millimeter thick PCB is 0.2 millimeter, 200 micrometers. So usually you can safely use minimum hole 200 micrometers, and then safe ring is 100 micrometers. It means the size of this via, size of this pad would be 100 micrometer plus 200 micrometer the hole and plus 100 micrometer here. That's 400 pad for this via. But Mike also explained on the outer layers, so for example on top and bottom layer, you can have this ring a little bit smaller. Do you remember how much you can have this outer ring? 75 micrometers. So basically, for example, if you need to make this via a little bit smaller under your BGA, because this clearance what is here right now it's too small, you can make this a little bit smaller. You can change this to 75 micrometers, 200 micrometers, 75 micrometers. That's in total 350 micrometers pad for the via. In Altium you do it this way. You select the via. Okay, I'm going to select the via, and here in the properties of the via, instead of using this simple, go to this top, middle, bottom, and here you can specify the diameter of the via on top layer, bottom layer, and inside of your PCB. So I'm going to change this to 35, oops, and also on bottom layer I'm going to change this to 35. In my design I don't really need 35 on the bottom, so I would maybe leave it 400, but because we were speaking about this in the video, that's why I changed it on the top and bottom layer. Now you can see I have enough clearance for this via under the BGA, and inside of the PCB on the other layers the pad is a little bit bigger. On the top is a little bit smaller, and inside of the PCB it is a little bit bigger. And this is a little bit safer and easier to manufacture this kind of via. From what we just learned, how we can apply this on via in pad. What is useful to know that we can make this top layer a little bit smaller? Why it is useful for via in pad? Because, for example, our BGA pad size is exactly 350 micrometers. So basically, what we learn is that in our design, we can use via in pad, which will have top layer size of 350 micrometers. We can take this via and we can place it exactly on the pad. Okay, of course we need to add a little bit more technology. What we will be speaking about what we have to do next with this via in pad, but we learn what kind of size we can use in via in pad. Now, what do you think why these top and bottom layer or these outer layers can be a little bit smaller than the inner layers? Do you know? Mike will explain in the next clip.
And the reason for that is, Robert, is that we've obviously got to register to the internal layers when we're drilling. And obviously all the material is going to stretch and shrink slightly differently. So having a bigger clearances or bigger pads
on all other layers, yeah,
it's easier to register, because the outer layers are then registered to where the drilling is, and it's all done with laser imaging. There's no more artworks anymore. It's all done with laser imaging. And that's why the internal layers, you need to have bigger clearances, bigger pads to allow for the registration.
That's really good note. So basically on the top you can use like lower tolerances, because you process the image and you know exactly, you can drill like almost exactly in the middle of the pad. But the inner layers, you can't see them, so they can be moved a little bit. It's better if the copper is a little bit bigger. Oh, that's interesting. That's really good. I thought the machines, they always just drill based on position. So it's not only position, it's also, they also have visual aid.
Yeah, correct. We only use lasers now, so even all our imaging for print and etch internal layers are all done with LDI, so laser direct imaging, no artworks, because we take out the stretch and the shrinkage of an artwork when it gets warm in sunny weather and cold in the winter time, and it reduces defects as well. So if there was any marks on the artworks, that will get superimposed onto the image. So yeah, it's all done with lasers now.
I googled for laser direct imaging, so you don't have to, and this is what I found. What exactly is LDI, laser direct imaging? When a circuit board is made, the imaging process is what defines the circuit traces. While the traditional imaging process requires a photo tool and UV light to transfer images, LDI only uses a computer-controlled, highly focused laser beam to directly define the circuit pattern in the board. How does it work? The panel is coated with a layer of photoresist. CAM files are preloaded into laser. The circuit pattern is digitally created on the board by CNC laser. Using acid, the areas that weren't exposed to laser beam are then etched, leaving intact the circuit traces. Interesting. Before I continue, there is something what I would like to show you. I know there are some recommendations in IPC standards about what kind of minimum via maybe you would like to use for different classes of your products. Class 2, they are kind of general electronics, for example, class 3, these are more robust designs, something for medical equipment or maybe some military or space, okay? And if I just googled for differences in these classes, I googled for an article or for a page where we could compare this minimum via between these classes. And here is a table for IPC class 2, and you can see that for standard, I'm going to zoom in a little bit, for standard PCB it is 62 mils, that's like 1.6 PCB, this is a standard PCB. For class 2 it is recommended to use at least 18 mil pad. If I put here 18, that's 0.45 millimeter. And for class 3 they recommend to have even like bigger minimum vias. For 62 it is 23, I'm going to put this 0.6 minimum via. Big difference. So one of the reasons why I started thinking why I don't want to use this reference design is because these vias are very small. They are even smaller than these recommendations from the IPC, because the IPC recommends at least 0.45. In our case, we cannot really use 0.45 millimeter because we would not be able to draw tracks between two vias under the BGA. So we will need to go to 0.4 millimeter, but I don't want to go to 0.35 millimeter as it is used in this reference design. And if you have a look on this reference design, they actually use these 350 micrometers on all layers. This is the top layer, but if I show you the other layers, you can see the via size is the same on all the layers. Okay, so I really didn't want to go this way. Now, this is the board what I'm designing. It is quite small board. It is only 47 by 60 millimeters, and I don't have to use the 350 micrometer through-hole vias which are in the reference design. I could use in this board the, let's say, 400 micrometers through-hole vias in this board, and it's not really necessary to use via in pad. But because this board is quite small, the price increase, if I decide to use via in pad in this board, the price increase is not going to be huge, and it is really good board to, it is really good opportunity to test this via in pad technology. So for example, in future, if I really need it, I can I will exactly know how to use it in these other boards. And also this is a great opportunity to create a video about via in pad. So this kind of board is really good example to show you how you can use via in pad in your own project. And that's why I decided to go with via in pad in this project, even if it's not really necessary. Okay, we know we would like to use via in pad. What now? There are more via in pad options. For example, we were speaking about via in pad which goes from top to bottom layer, so about through-hole via in pad. But there are also via in pad which can only go between different layers. And as an example, I'm going to use this different project. This one is not using via in pad, but it is using the kind of vias, and it is using exactly the stack up what I'm planning to use in this board. So what kind of vias I'm thinking about to use. We are speaking about through-hole vias. Okay, don't forget, when I'm speaking about via here in this design, it is same as, or we can use same kind of via also as via in path. So imagine this as via in path from top and bottom layer in our new design. And then we have also these smaller vias, and these are microvias. And again, in this board they are not used as via in path, but in our board we can use it also as via in path. This microvia, it doesn't go from top to bottom, it only goes from layer 1 to layer 2. Okay, I'm going to click on layer 2, have a look. So here is the microvia from layer 1 to layer 2. On this layer 2, it is connected to different microvia, and then it goes on layer 3, and then I'm using also buried vias which are inside of the PCB. If you have a look at cross section of the board, this is how it looks. Okay, this is the through hole via, this is the microvia or blind via from layer 1 to layer 2, this is from layer 2 to layer 3, and this is the buried via which is inside of the PCB. It is buried inside of the PCB. So in our new design, I would like to use via in path, through hole via in path like this, and then I would like to use also via in path or microvia in path like this. But I would like to know what is the minimum drilling and what is the minimum path for this kind of a microvia in path. And we are going to speak about this also because in some very small BGAs, you cannot really use this through hole via in path. You will need to go with microvia in path, because these microvias, they can be much smaller than these through hole vias. And as I said, now I'm interested to know how small these vias in path or microvias in path can be, what we can use and what are the limits when a PCB is manufactured. And that's what we are going to speak about in the next clips.
Minimum size of the pad. Ideally, we were looking for 50 micron annular ring.
Okay.
So if it had 125, and then 225, so you could have a minimum 225 micron BGA pad.
Okay. And how deep you can drill if you use 125 drilling?
You can have 100 micron dielectric.
Okay, so the next layer basically can't be further than, or the pre-preg thickness can be like 100 micrometers.
I mean, a rule of thumb really is that you want to have the aspect ratio of 0.75 to 1. So if, let's just say, for instance, you had a thinner dielectric, because you got to take into consideration the thickness of the pre-pregs that are available. So, and very common is a single ply of 1080 pre-preg, which is roughly about 75 microns thick. That would allow you then to have a minimum microvia ablated size of 100 microns. So your BGA pad then could be down as little as 200 microns.
Let's have a look at these numbers again so we can remember them better. And I know we are speaking specifically about Exception PCB, but don't forget all the other advanced PCB manufacturers, they use exactly same machines, they use exactly same technology. So these numbers, what we are talking about, they will be very similar for all these other PCB manufacturers. So if you follow these numbers, what we are speaking about, you will be probably able to manufacture your PCB even with all the other advanced PCB manufacturers. And I've got this very nice document from Exception PCB, and here are all the kind of limitations what you may want to follow when you are designing your PCB. And because we would like to learn more about the minimum microvia, what we need to look for, what kind of numbers we would like to know. Do you know? We need to know the minimum annual ring, what we can use for microvia. So I'm searching for these numbers here, and here it is. Annual ring on outer layers, on the top layer, for microvias is, for standard processing, 75 micrometers. For technical processing, so this is maybe, this can make maybe your PCB a little bit more expensive. These are the kind of limits maybe what you don't want to go lower. For annual ring outer layer microvia, the limitation is 50 micrometers. Okay, so this is the minimum number for a ring. What else we need to know if we would like to calculate the minimum microvia what they can manufacture? We also need to know the minimum hole what they can drill to this microvia. So I'm going to search for this information. Here is drilling. Laser drilling for microvias. Standard processing 125 micrometers, technical processing 100 micrometers. So what is the smallest microvia what we can create? 50 micrometers the annual ring, 100 micrometers the hole, 50 micrometers the ring. In total, 200 micrometers. That's exactly what Mike said in the video. That's the smallest via in path. That's the smallest path what you can use, 200 micrometers. If you were listening carefully what Mike was talking about, he also mentioned this aspect ratio, and this is a very important number. And I would like to speak a little bit about this aspect ratio, because I know that many people, they never heard about this, and it is very, very important. This number is telling us how deep you can, or how deep your vias can be for specific hole size. Okay, the thing is, there are some limitations when vias or microvias are manufactured. There is process what is called plating, and this plating is putting the copper inside of the vias. And if the hole would be too long and too small, this copper, during this process, the copper will not go through the whole length of the via. Okay, so these numbers what you can see here, they are telling you how small the hole can be for specific length, and when this via can be manufactured safely. What does it mean for our smallest path, 200 micrometer path, or the via in path, which is using this 100 micrometer drilling? Do you know what does it mean for us? It means that if you use this smallest 100 micrometer drilling, and when you consider this aspect ratio, which is down here for microvias, by the way, I think this is a mistake, okay? I think even Mike mentioned in the video it should be 0.75 to 1, okay? This 0, which is here, is wrong. It should not be there. So if you consider this minimum 100 micrometer drilling, and you apply this aspect ratio on this drilling, you can easily calculate what is the maximum thickness of the pre-preg, what is the maximum distance between the layer 1 and layer 2, what you can use on your PCB for this smallest path. How we are going to calculate it? What is the maximum thickness of the pre-preg? Calculation is very simple. Okay, 100 micrometers hole, just multiply by this number which is here. So multiply by 0.75, okay, that's the correct number, and that's 75 micrometers, okay? So the maximum distance between two layers where you use this 100 micrometer drilling can be only 75 micrometers. Distance between layer 1 and layer 2 for 100 micrometer drilling can be maximum 75 micrometers. If your stack up is different, if you have like 100 micrometers between layer 1 and layer 2, you need to use bigger hole in your via. Very, very important. We have learned a lot about standard vias and standard microvias, but we would like to learn about via in path. What is the difference? Difference is that you take the standard via or standard microvia and you place it into a path. But you cannot use it like this. What you need to do, you somehow need to place copper on the top of the via, so you can nicely solder the components on the top of the path. If you don't put there the copper, then there would be the hole. And there are more options how you can do it. Exception PCB, they send me these very nice pictures where we can see, for example, that one of the options is fill up the via with resin and then overplate these kind of vias. And when you overplate these vias, then you will put this copper on the top of the via, so you will get very nice path on the top of the via. Or sometimes they call it capped vias. A different option is, for example, copper filled vias. So this is the standard through hole via, which was filled up, completely filled up with copper, and then you make the top of the path, you make it nice and flat. We will be speaking about this, how you do it, how these processes are done. And here on this last picture, you can see buried via, copper filled buried via, and on top of this via there are two copper filled microvias on top of each other, or sometimes they call it towered microvias. Okay, in the next clip we are going to speak about these filling up these vias in path.
Okay, so if we go, we'll just cover the resin fill and overplate option. So again, the minimum, it's really the aspect ratio of how thick the substack can go through. But our minimum drilled hole size for resin fill is 0.2, so 200 microns. Because then that allows then the vacuum assisted resin fill system to fully fill the plated hole. Because we have to drill those holes first, then plate them, and then resin fill, and then plate over the top.
And so the ratio would be like 1:10, or sort of, for a 1.6 PCB, the 0.2 is fine.
Yes, you're looking at an aspect ratio of 8:1, which is fine.
Okay. And when we are speaking about the filling, I read you can use like epoxy filling or some conductive filling. What is your experience with this?
We have two options. Most common is epoxy resin fill, because then that can run through our mass vacuum assisted system. So then resin fill, cure, planarize the surface to make sure we remove any surface resin, because that is a big problem if you leave any resin spots on the copper surface, and then plate over. The other option that we have, just for exception, others may well have conductive paste. We don't use conductive paste. We prefer just a copper fill.
Okay. And can you do like copper fill inside of these through hole vias?
Yes. Yes.
And they will be like completely filled with copper?
They're completely filled with copper, yes. The only constraint really is time, because to fill a through via with copper could be anywhere from 24 to 48 hours.
Wow. So it is also much more expensive than epoxy fill.
cost-wise, it's not massively more expensive. It's just a time constraint that yeah, we have to grow the copper back into the barrel of the hole at a low current density to avoid trapping any solution or air in the middle of the hole.
Okay.
Because what will happen is obviously the hole will close quicker at the knee of the hole.
Air trapped inside of a via? Interesting. When PCB is manufactured, sometimes may happen that air will be trapped inside of this via. And it doesn't have to be during, or it doesn't have to be when we are creating, for example, via in pad. This situation can happen also when, for example, solder mask will flow into via and it will plug it from the top and from the bottom. Then air will be trapped inside of via. Or, for example, when you are building PCB, this prepreg can melt and it will not flow completely through this via. It will somehow stop only here and then here, and it will trap some air inside of via. And we really don't want to have air trapped inside of via because it can cause some problems when the PCB is heated up. For example, when you are assembling board, you send it into oven, PCB is heated up. This air can expand and it can kind of, for example, explode. Yeah, it can damage the PCB, or it can damage the connection what is on the top of via in pad. It can damage the BGA ball and there will be no connection. Okay, so we really don't want to have air trapped inside of vias. And it used to be a problem, so I was curious to know if it's still a problem or what are Mike's thought about this kind of situation, about this kind of problematic air trapped inside of vias. And that's what Mike explained a little bit in the next clip.
It really is it's the development of having the resin fill systems, because before the air that before I would say that it was probably a case that manufacturers would allow the prepreg that was going to be bonded on top to flow into the hole.
Okay.
And if you've got a large number of holes, the prepreg, like I say, typically is a thin prepreg. It was not sufficient to fill all the holes 100%. And that's where you would then end up with some air entrapment in the center of the hole.
But now it's okay, or?
But now it's okay because most manufacturers will have a resin fill system to assist in that process.
Okay, so we don't. If we decide to go for via in pad, we should not be worried about problems during manufacturing or assembly.
No.
Interesting. If you have a look at this picture, you can very nicely see that this via here, it is actually filled up with something, because this is the prepreg. Can you see the prepreg? And it is very nicely on top of this via. This via is filled with something else. Nice. By the way, this on the top of the PCB, this is just solder, okay? So you can just ignore this. And when we were speaking about different kind of filling for the vias, I wanted to know if there is some difference between reliability of filling up vias with copper, or if we use these resin filled vias, because I read some articles that there may be some difference in reliability. So I asked Mike.
Yeah, I mean, there are several white papers on that. It's because yeah, if you're using an epoxy fill, the resin is of the same makeup as the resin used in the prepreg for bonding. Obviously, if you go for a solid copper fill, then you've got a different thermal coefficient of the copper expanding at a different rate to the FR4 dielectric, the prepreg, and the cores. But the only time that we have seen this as being problem is mainly if you put the microvia directly on top of a buried via. Whether that buried via is copper filled or resin filled, under thermal constraints, i.e. the application of the board, if the chip is going to run very hot, it can cause obviously the PCB to expand, and what can happen is you end up with what, as they call it, an eyebrow crack. So the microvia separates away from the buried via at high temperatures, so expansion, it goes open circuit. When the unit cools down, it goes closed circuit and then is functional again. Okay. And that is why you'll see, if you've probably seen several white papers on what they call eyebrow cracking, and trying to get designers to stagger the microvias away from the buried vias. And also, in some instances, because some of these BGAs are, you know, we manufacture boards that are using 0.2 pitch BGAs, and the only way they can fan out is to go to a towered microvia. And again, towered microvias, you know, we manufacture a considerable amount here on a daily basis, but that is always going to be the risk is of when the board receives any high thermal shock. So if the PCB is, let's say for instance, it's in a drone and it's going to be on the ground in a high temperature country, and then it's going to go into the sky, the temperature is going to drop quite dramatically. It's that thermal excursion and pressure on the PCB that the PCB is going to start to expand and contract.
So what did we learn from the previous clip? That if you don't have to, maybe you don't want to place microvias on top of buried via, or you don't want to maybe place microvias on top of each other, because this may influence the reliability of your board. Mike explained that if you place microvia on top of a buried via, you can get something what is called eyebrow crack. Okay, and I think this may be what he is talking about. This is what we can see here on top of this buried via, and on top of or bottom of this buried via there is some kind of inconsistency, and maybe this is the crack which can kind of appear between the buried via and the microvia. And same probably can happen also between these microvias which are here. And these are the towered microvias, they are put on top of each other. So what you can do, I will open my previous design. This is what I normally do. So I place the microvia somewhere, and on the second layer, on layer 2, I connect, I make very short connection to different microvia which goes on layer 3. Okay, I don't place the microvias on top of each other. Now, many people ask why we cannot just go from layer 1 to layer 3 with the microvia. Do you know? We were speaking about this. If you would like to go from layer 1 to layer 3, it will be much longer distance. When we use much longer distance, what is going to happen with our microvia? Do you know? We have to use bigger hole. And if we have to use bigger hole, then I don't really need this small microvia here, because what I really need is the space on this layer 3, which I can save when I'm using these microvias. I will get a lot of space when I use microvias on layer 3. I don't want to use big, huge microvias. And that's the reason why I go from layer 1 to layer 2, and then from layer 2 to layer 3, because then I can use small microvias. Okay, in the next clip, Mike will say his own opinion about using these stacked microvias.
If the design constraints allow the microvias to be staggered away from each other or away from any buried sub, I would recommend that that's the best way to go.
In the next clip, we are going to speak a little bit about filling up the buried vias. Then we will speak about resin-filled vias versus copper-filled vias and the BGA. And we will be more specific about my board, about my project, what Mike would recommend, what kind of through-hole via in path Mike would recommend for my board.
It was, if we were manufacturing, is that we would introduce the process step of resin filling before we bond the subsequent layers on.
Okay. So what you are saying, basically, these buried vias, are they always filled, or you need to ask to fill the...
Predominantly, we tend to fill all the time.
Okay, so even if people don't ask to...
If people don't ask, we would resin fill.
Okay, but for like through hole vias, you need to do something special, yeah, because there is no pre-preg.
No, for through hole, yeah, we have the two options. It would either be resin fill and overplate, or 100% copper fill. But like I say, the constraints around that then is the aspect ratio. I would say that the most common is if it's in a BGA pad, the most common, or our recommendation would be to copper fill. If it's not in a BGA pad, resin fill. But I say when it's not in a BGA pad, if the through via is in an SMD pad, so it's a larger footprint, I would recommend using resin, because the resin will shrink very slightly. You may get a 10 to 15 micron dimple on the surface, which is probably acceptable on a SMD pad, but if it's in a BGA pad, that may cause assemblers a little bit of concern putting the ball onto a pad where there's a dimple in there.
Okay, so
if you're having if you're having a through via in a BGA pad, I would recommend copper filling. Have a through hole in a larger SMD pad, I would recommend, or we would recommend using resin fill.
Okay, so for this kind of design, what I'm thinking about, if I would like to place these through hole filled vias into power pads, I should use the copper filled PCB.
Yeah, correct, Robert. Yes, I would go for that version. I think you'll get a much more robust. Yes, it may take 2-3 days longer to manufacture, but the end product would be far more robust.
Okay, we have learned that in this my project, I can use through hole via in path, which will have this top via size 350 micrometers. It is exactly the size of the path for my BGA, and then this through hole via in path would have 400 micrometer path size on all the other layers for easier and maybe cheaper manufacturing. And also we learned that because it is under BGA, we would like to copper fill these through hole vias in path. Now my question was, if I need to somehow show or mark the location of these through hole vias in path, if I need to somehow show this location in the documentation for PCB manufacturing, or how can I do it? How can I tell PCB manufacturer where these vias in path are located? And that's what is this next video about. Mike is going to explain how you can do it, how you can show where these vias in path are located.
If it's a buried via, we would either resin fill or copper fill all of them.
Yeah.
Yeah. If it's a through via, we can be selective. We have to be selective anyway.
Okay.
Because whether it's copper filled or resin filled, the vias that we need to fill are separated on the drill program. Now, what we do see, or some customers will do, is that they will actually change the drill size. So let's just say, for instance, Robert, you've got I forgot what I was going to say now. 200 micron via through vias across the whole board. Now, but only in certain areas do they need to be copper filled. If it's easy for you, you could set those vias at 201 microns.
Okay.
Actually separates it out on your drill program.
Okay.
And then those holes, we drill those only on the panel. We then plate the barrel of the hole, and then we'll either resin fill them or copper fill them. And what we do, we create a mask to just expose those holes which need to be either resin filled or copper filled. So then we would then run that process of filling them. The process after that then is we do need to have a planarization, because we've got to take the surface copper back down, otherwise you'll end up with bumps on the where the holes are. We then drill the remaining plated through holes and go through the process again.
Okay, but you drill all the holes at once, just how they are filled?
No, if they're through vias, we have to just drill.
So you have to drill twice then.
Yeah. So in essence, what you end up doing is you end up having two drill programs. You end up having two lots of plating, and that's where the cost goes up slightly higher, and the lead time, manufacturing time, goes higher because you've got more processes to run.
What we have just learned from the previous clip. We learned that for the buried vias we don't have to specify anything. All the buried vias will be automatically filled up. But for the through hole vias, we need to tell PCB manufacturer which of these through hole vias we would like to fill up. They are not going to fill up all the holes on your PCB. Yeah? You need to tell them which vias or which drillings, which holes are the holes what they need to fill up. And as Mike explained, very simple way how you can do it is change the hole size a little bit. So for our through hole via in path, which we will use here under BGA, we will change the hole size, and instead of using standard 200 micrometers, we will use 201 micrometer. Now, because Mike mentioned they will be doing this in two different drilling processes, I wanted to know if they need two different drill files. And I wanted to ask this because usually these CAD systems like Altium, they generate only one drill file. I wasn't sure how I would generate the second drill file. So I asked Mike, and this is his answer, if you need to send them only one or two drill files.
In the engineering cycle, when they're doing the full DRC check, they will highlight those holes which are in CAD. And split that onto its own drill program.
Okay, so one drill file is just fine for you?
Yes.
And in the next clip, I asked Mike what else we need to include in PCB manufacturing documentation so PCB manufacturer can manufacture your PCB with vias in path correctly. What else they need to know about vias in path in your PCB? Here is the clip.
It is useful to have some kind of balloon drawing or demarcation, identification markings to say these vias need to be either copper filled or resin filled on the drawing. So yeah, a comment on the drawing to say vias in pad to be copper filled.
I don't know exactly yet how I'm going to do this, but it will be probably something like place drill table, maybe something like this. And because the hole size for all vias in path will have some specific dimension, then all these vias in path will have same symbol, and somewhere in the notes I will say vias in path to be copper filled, something like this. I don't know exactly how I'm going to do it, but this is just an idea, so maybe you get some ideas how you could do it in your own CAD system. When you will be looking into this topic, into via in path topic, you may find out there are actually more via types, how these vias are covered or filled up. And there is IPC standard. If you Google for something like this, and when you click here, you will find some kind of specifications of this kind of processes, what you can do with vias, so you understand better what are the differences. Okay, so when someone says they would like to plug vias, it is different than when you would like to fill the vias. And if you go through this IPC specification, you can see here are the different types of vias. Like type 1 is just tinted via covered with mask, or it can be plugged via. Okay, you can plug it only from one side or from both sides. You can see this is again something different, like plugged via with solder mask. And here are the filled vias, again different kind of filled vias. This one is just filled, this one is also covered, this one is also overplated. Okay, so there are different types of methods what you can do with the vias, and I wanted to mention this. So when you read about this kind of topic, vias in path, and when you see all these names like tinting or plugging or filling, then you understand what is this about and what are the differences. So as I said, in the next clip, Mike is going to speak about this a little bit.
But yeah, a plugging typically is for solder mask. So you would only partially plug vias because the solder mask process is probably never going to give you 100% fully plugged via.
And what does it mean? It means like you put thicker solder?
In essence, yeah, it is a solder mask resin that goes on, and we apply that on through a screen. Our application will fill the via probably around about 60% of the hole.
And why people would use it? Is it like because then inside of the via is...
It's cheaper.
Okay.
It's cheaper, it's quicker. It's not a problem for the PCB manufacturers, but it does present problems for assemblers because there could be any moisture or anything trapped in the part of the via that isn't filled, and then that can cause problems when they go through assembly.
So normally people don't want to use plugged vias, yeah?
No. We, like I say, we recommend we will discuss with the customer if they say they want plugged vias. We will either offer them the option for just resin fill. They don't necessarily have to be plated over, but resin fill them. Because even if we plug from both sides, we can't guarantee that there won't be air entrapment in there.
Okay.
When it goes to assembly, the board is going to be heated up.
I understand.
It's just going to blow the plug off. So we either like to have the vias fully plugged or fully open.
This is interesting. You know what Mike is talking about, yeah? These are the situations when you, for example, tend vias from both sides. There is air or solution or something else can be trapped inside of the via. Or when they plug the vias, again, there can be something trapped inside of the via. But then, I always tend my vias on all the PCBs. Tented vias, it means there is mask on your via. Okay, there is the green color on the via. And because I always do it, I heard some people that they actually create a small hole on the top of the via so this solder can flow inside of the via. And I wanted to know if they do this automatically in PCB manufacturing factory, or if engineers have to do it to be sure that there will be nothing trapped inside of the via. So my next question to Mike was if we have to put here the small holes, or if we don't put here the small holes in manufacturing output, then what they do in the PCB factory. And here is the clip.
We see several options on that. Yeah, obviously some customers want to have, as they call it, tented or mask over all the vias.
Yes.
Yeah. The solder mask nowadays is obviously liquid, so it will flow into the hole.
Okay. But it's not going to plug the via. It only flows inside.
No. And hence why what we would do is that, we would create a small pad on the solder mask to expose, so we can flush the solder resist through and out of the hole.
Okay, so even the via is tented, there is still a hole.
Yes, it is tented, but there will be a small witness around the via, plated via, of exposed metal.
Okay, and you always do this small hole in the mask, or not always?
No, not always. It really depends on what we see from designs. But where customers have, they want the via tented on one side and open on the other, on the side, maybe for testing, we would put a small hole in the top side to allow the solution through.
Okay, and if they have tented vias on both sides, do you put there the holes or not?
No.
And it will automatically, there will be the hole anyway.
But there is obviously, if it is a very small hole, there is a chance then that the solution would develop fully out of the hole.
And what does it mean, very small hole? And is there then a risk of the air trap inside, or?
There is, yes. Again, if you're going below 250 micron via, there is a risk. So if we see that as a risk, we would then put a small clearance to allow the solution to flush through.
Okay. In the next clip, I wanted to know if there is difference in quality of the pad between using this copper filled vias in pad and resin filled and overplated vias in pad. If this pad quality is different, and as you can see even from this picture, there actually is some difference between quality of the pad. But watch the next clip. If I understand, like capped vias are, you fill them with epoxy and then you put copper on the top, or?
Yeah, resin fill and overplate, as we call it, yes.
Okay, and how is it different comparing to copper filled? Is it like cheaper, or it's not as good as copper filled, or?
It is more cost effective than copper filled, and it is a quicker process.
Is the surface same quality as copper filled, or?
No, because you'll end up with somewhere in the region of maybe a 10 to 15 micron dimple in where the resin filled holes are.
Okay, so copper filled are always better for vias in pad under BGA.
It is virtually 100% flat pad surface.
And then I had to ask how they actually create these copper filled vias and how they make the surface flat. And Mike will explain in the next clip.
Yeah, the process is that if we were copper filling, we would again drill the holes, plate them. We then put it on our CVF line. So we create a film which will just expose the holes that need to be copper filled. So we create a film which has got a 25 micron annular ring, bigger than the hole. We put that mask on and then we put it into our copper fill tanks and slowly fill the copper back into the holes or the microvias.
I understand it. And then?
Once that has finished, we remove the film and you'll end up with a small dome of copper on the surface, like little dimples.
Mm-hmm.
We have to then use our planarizer, which is like a semi-automatic hand sander, to planarize those dimples flat.
So you kind of sand the...
You sand both surfaces flat.
And you can't do this on these capped vias, or you do it also on the capped vias?
It's the same process for the capped vias. Yeah, same process.
And now, the most important question. How much it is going to cost? How much more expensive my PCB will be when I use these resin filled or copper filled vias in pad? Here is the answer.
You're probably looking for, if it was resin filled, probably about a 30% cost more. Copper filled, maybe 60% more.
Okay, that's quite a lot actually.
It is, but it also depends on how many circuits are on a manufacturing panel.
And does it depend on number of vias or?
No, because it's done across the whole manufacturing panel. The resin process or the copper fill process is across the manufacturing panel. Whether you have 10 holes that you only need filled or you have 200,000 holes that need filling, it's the panel that goes into the process.
Yeah, I understand it.
So it's per panel that we have to look at. So, but there is a cost. It is a difficult one, Robert, to say. I can't say that, it's going to add exactly 25% to the board cost because it depends on the number of manufacturing panels that we have to do, and then that cost is basically split between the final number of circuits required.
Now, I played the clip a couple of times and I think I understood like 30, 30 and 60, 60, but if I'm wrong, just tell me in the comments. Still, this means that when you are designing small PCBs like computer on module, small PCBs, price of these PCBs is maybe somewhere between $10 to $20, and this kind of increase, 30 to 60%, is not so much for so small PCB. But if you would like to use these vias in pad in large PCBs, then it can cost you quite a lot of money. Okay, so this is something what you may want to consider. If you are designing large boards, maybe don't go into too high technologies, because then your PCB can cost a lot of money. But for small boards, you can do basically, you can use any kind of technology what you want. Okay, we learn almost everything about these vias in pad. I was still curious to know, because we were speaking about the pads under BGA, I still wanted to ask question about mask opening. how small mask opening is recommended to use around the pad, because usually there is not really much space under BGA, so the mask opening you would like to use maybe as small as possible, and I wanted to know what are the limits. So here is the clip where Mike was speaking about this mask opening around the pads.
Typically, what we see as, if you like, a standard is a 50 micron annular ring. So if your pad is 350 microns, your solder mask opening, if it was going to be clear, would be 450 microns.
So 50 and 50.
Yeah, but that then may leave you with only a very small sliver between the solder mask. So the option there is then to take the solder mask opening down to 400, so we have a 25 micron annular ring. So it's just tighter registration, because the dam, if you like, or the sliver web between the pads typically really should be no less than 75 microns. Otherwise, going through the development process, you may well develop it out, which then may cause some solder bridging across from pad to pad.
Okay, that's interesting. I usually use 0 or 100 micrometers. It's good to know you can go down to 75. Is it going to influence the price of the PCB, these tolerances? No. It's still same machine. And okay, so even if you go like from 50 to 25 micrometers bigger, it's still not going to...
No significant cost. The only thing is then that we need to use our laser direct imaging to get the registration, because it's obviously a lot tighter.
To give you visual interpretation of what we were talking about, I used 100 micrometer bigger opening on these two pads. So this is what I normally use, okay? This is the pad, and this is the solder mask opening, which is 100 micrometers bigger. It means it is 100 micrometers between the end of this mask and end of this pad, which is here. When I click on this pad, you can see it specified here, okay? Solder mask expansion, 100 micrometers. Now, what is sometimes problem under BGAs, or when you have the pads very close to each other, the problem is this space between two openings around the pads. This space, which is here, it will have very small, very thin solder mask. This part here, it is called sliver. And as Mike explained, maybe you don't want to have in your PCB this sliver smaller than 75 micrometers. So if you see something like this, very small sliver, you can make the mask expansion smaller. And Mike explained you can easily go down to 50 micrometers. So this is how it looks when you go down to 50. That's what I use in my footprint. And if you need, you still can go even smaller. You can go down to 25. And then it would look like this. Okay, I hope you found this information useful. We are almost finished. There is one more question what I wanted to ask, and it's about the minimum distance between two vias, or to be specific, it's not really about vias, but it is minimum distance between two holes. This minimum distance between two holes will specify how close you can actually place the vias. And the answer is in the next clip.
All right. Minimum hole to hole of 200 microns.
For any kind of hole?
Yeah.
Okay.
And if you have a buried via and a microvia tracked away from it, you can come down to 100 microns.
So 200 micrometers between holes on your PCB. And we are almost done. This video is almost finished. I would like to say this was not an advertisement. As I explained on the beginning of this video, we have been using Exception PCB for years, and we used Exception PCB for several reasons. One of the reasons is, for example, they are located in the UK, so basically because we are in Europe, it is very easy for us to talk to them same time zone. They are close to us. We also use Exception PCB because many times we had to manufacture prototypes, so like maybe 5 or 10 or 20 PCBs, like very advanced PCBs. And some PCB manufacturers, for example in China, big PC manufacturers, they didn't want to talk to us about manufacturing so small quantities for prototypes, and Exception PCB, they manufactured these boards for us. And they also manufacture, our company Fedevel, we don't manufacture PCBs, but the boards what we have designed are manufactured and sold by Voipak. And I know Voipak is buying many PCBs through Exception for their products. So Exception PCB, they can do the prototypes, and they can do also standard production of PCBs. I need to say, I know, or I asked Mike about if they still have the manufacturing in the UK, and Mike confirmed, yes, they still have manufacturing in the UK, but a big PCB manufacturer from China, they bought them. So what they also can do, they can kind of arrange PCB manufacturing through companies in the China, so you can get a good price for your PCBs. Again, this is not advertisement, this is our experience with working with Exception PCB. Yeah, I really would like to know your feedback. I would like to know if you liked this video, if you found it useful, if you learned something new. So please leave your comments under the video. Let me know what else you would like to learn about PCB manufacturing, and it's important, it's always important to give me this kind of feedback, like leave the comments and like the video, because it motivates me to create these kind of videos. They are not easy to create, and also I use these videos, I use your feedback on these videos to contact other people. I will show them, like, we can create video about some kind of simulation about something else what otherwise would be very difficult to create. I will always tell them, have a look, this is the kind of video what I created with this person, and you see, people like this kind of content because you view it, you like it, and then these other people are willing to create new videos about interesting topics which otherwise I would not be able to create. So don't forget, leave comments, like the video, and see you next time. Thank you very much.